afternoon, and once more, Mr. Rector, distinguished guests, ladies and gentlemen, welcome to the 12th lecture dedicated to our late colleague and friend, Professor Andrzej Lasoty. Today's lecture will be delivered by our distinguished guest, Professor James Alan York, who collaborated with late Professor Andrzej Lasoty on several works, on several papers. So let me now ask the former chairman of the chapter of the lecture, who chaired the chapter for more than 10 years, I guess, Professor Roman Ger, to say a few introductory words about the cycle of the lectures itself.
Thank you very much. Our distinguished guest, Professor James York. Actually, I am a bit frustrated, because I don't know what I'm doing behind this table. That's actually, since last year, Professor Wykład became the chairman of the chapter. And nevertheless, our faculty council decided once that I should become an honorary chairman of this. And on that base, I would like, don't be afraid, only a few words, and to tell about Professor James York, because it was my idea as I was the chairman to invite Professor York as a lecturer for this period, for this series of lectures long time ago, for different reasons. It couldn't be realized, but right at the end of my, say, cadency or whatever, it happened that after my subsequent invitation, Professor James York finally accepted our invitation, for which, for that we really are very, very grateful, because it's, I believe, all of you gathered here know that he's an outstanding scholar, and actually, as the dean told already, worked together with Andrzej Lasoty for years. Andrzej Lasoty was visiting the University of Maryland for several times and for some years altogether, and they were working together, writing deep, interesting papers. Actually, yesterday, I was honored to be invited to some semi-private meeting with Professor James York, during which he told me that he treats himself as a student of Professor Lasoty. Well, I'm just repeating. I wouldn't dare to say it on my own. Anyhow, I would prefer to say a close collaborator. But anyhow, it's great honor to hear that Professor James York treats himself as a student of Andrzej Lasoty. By the way, if I am not mistaken, Professor York has 50 PhD students, around that, which is enormous number. That's something which it is difficult to believe. So he really has an army of students that lecture. But more details will be talked about Professor York by Professor Łukasz Stedner, who is the present chairman of the chapter of this lecture. And let me finish my unprepared social talk, with expressing once more our deep thanks that you, Professor York, accepted our invitation finally. So we are very happy to have you here and to listen to your lecture. Thank you very much.
Thank you very much. So now I ask Professor Stedner to present, to introduce our distinguished guest to the audience.
So, ladies and gentlemen, let me first say a few words about lectures. This is the 12th lecture. We have every year starting from 208 lectures. And let me list the names of successive speakers. It was Professor Czesław Olek, Michael McKee, Professor Andrzej Pelczar, Lech Górniewicz, Jean Małę, Łukasz Stedner, Tien-Yen Lee, Profesor Roman Strzednicki, Profesor Aligo Cielina, Profesor Aleksander Weron, Profesor Piotr Biller. So, now coming back to our 12th speaker, Professor James Alan York is a distinguished professor of mathematics and physics in the Institute for Physical Sciences and Technology at the University of Maryland. He has a wide range of interests, starting from chaos theory, weather prediction, genome research, population dynamics. He wrote 3 books on chaos and 1 monography. Professor York received Dr. Honoris Causa degree from University of Juan Carlos Madrid in Spain, and then from University Le Havre in France. In 2013, Professor York retired as a chair at the University of Maryland, the Maryland department. As already was told that he supervised 50 PhD theses, and he wrote over 300 publications. Among them I found 8 joint papers with Professor Andrzej Lasota, some of them extremely frequently cited. In fact, let me say that the most frequently cited paper of Professor Lasota was written with Professor York, and this is a paper, Existence of Invariant Measures for Piecewise Deterministic, Piecewise Monotonic Transformations, which appeared in Translation of American Mathematical Society in 1973. The number of citations, it was 489. This is the number 2 days ago. But let me say that Professor York has enormous number of citations. I even checked, and this is the most cited paper, which is really interesting. It's close to my real interest, scientific interest. It's a paper Controlling Chaos with Ott, Greboki, and York, which appeared in Physical Review Letters. And the number of citations 2 days ago, it was 4,536. So it's a really great big number, and also other papers. So I'm very honored and I'm privileged to announce that the 12th lecture of the memory of Professor Andrzeja Lasota will be delivered by Professor James Alan York, and the title of the talk will be Multi-Chaos. Okay, floor is yours.
My turn. I'm delighted to be here. Your introduction reminds me of a joke of Lasoty's. Someone told him, "I have 300 papers, how many do you have?" And he says, "Well, I have fewer than you, but I have more than Einstein." Actually, but nobody knows how many papers a baby has, so it's not the number of papers, it's are people paying attention. And he and I like to look at simple questions. I think we were very good friends, but when he came to Maryland the first time and I met him, I guess, I don't remember exactly what year it was, but it was right around when I got my PhD from the University of Maryland. So I've been at the University of Maryland since 1963. But I got my PhD, and I don't think I was very well educated. And so, for example, we started working on ergodic theory. And I had no idea what these ideas were, so that's why I'm saying that he was really a mentor. And here is a picture I took in, I think, 2002 of Lasoty and his students. And also there I have a little outline. I'm going to talk about 3 results that I proved with him to demonstrate the variability of what we did. We had perhaps a dozen papers. But I picked 3 papers which are relatively easy to describe. And I'll talk to you a little bit about what led up to them, and then I will tell you some current work. And one of the advantages, when one gives a seminar in a technical meeting, you have to restrict yourself to the most current stuff that you've been doing. Last month I was in India and I gave 5 lectures, but they were mainly to students from around India. And so I could talk about whatever I thought they should know, as opposed to what's the most current, because things get forgotten and the students don't know. So in any case, I've been playing with the name of what I call multi-chaos, and I will get to that, but I also call it heterogeneous chaos, and one of my collaborators said, why call it hetero-chaos if you could call it homogeneous chaos? And I don't know. So, if we look at basic differential equations, one question that came up a long, long time ago is whether or not they have solutions. And here I have put down a Lipschitz condition, this condition number 2. And if it satisfies a Lipschitz condition, even in an infinite dimensional space, then there will be a solution of this differential equation. game. You have to pay attention. So here's a theorem, part of a theorem. So we assume we have a periodic solution with period p of this differential equation. And we assume that the norm is Euclidean norm, the Euclidean distance. And we have a Lipschitz constant, number 2. And the question is, what's the theorem? What is implied by this? What do you mean? You haven't assumed anything. So what is the theorem? Now, I don't know how to hold this upside down. Theorem. The period is greater or equal to 2 pi over L. The Lipschitz condition is usually used to talk about how fast trajectories move apart. They move apart with exponential speed. But this is a totally different use of the Lipschitz constant. And what it's saying is the trajectory can be turning in space, but how fast it can change direction is limited by the Lipschitz constant. And this was a new idea. And I told Lasoty about this result. This was published 50 years ago. And so I've copied here at the top of the page. And so Lasoty came up with another idea as to how we could change this. So this is how one of the many ways in which we collaborated. This is Andy. He wanted to be called Andy in America rather than Andre, but Andy's a nice name in any case. This is in the parking lot of our institute. And he says, well, if we look at any norm instead of the Euclidean norm, then he could prove the period is greater or equal to 4 over L. Remember, the other theorem said 2 pi, roughly 6 over L. And for the Euclidean norm, if you take a linear differential equation and something goes around in a circle, it's a perfect, the original theorem is a perfect fit, but this is for any norm. And so we wrote a paper. And now as I look back at the paper, we have about 4 different results, but this is the only important one. It's simple. And I may have come up with the other 3, which are not important. At least it's a nice result that he came up with. And later on, it turned that the number 4 could be improved to the number 6. But it was the idea of doing these things that was particularly nice. Okay, I talked about the existence of solutions. Well, it's not such an easy question. In finite dimensions, if you have a differential equation, x dot equals f of x, and f is continuous, then there will be solutions. But infinite dimensions wasn't so clear at the time. Jean Dieudonné had given an example, very strange example, very simple example, where he gave a differential equation which had no solutions in a particular Banach space. But you could write down the solution, but it wasn't in the space. It was in a different Banach space. It seemed weird. So why not just take Euclidean space, namely Hilbert space, and I proved that you could have a continuous differential equation, and here's an initial condition. You start from the origin, and there's no solution. Okay, so this is the start of our second paper I'm going to describe. So this says that there's no solution on any interval. So So we came up with the idea that almost every initial condition would have a solution. We could prove this. Almost any in the sense of bare category. So we take a result where we show there's no solution, but this wouldn't lead you to think that there would be some result. And strangely enough, he and I came up with this result which says that almost every initial condition will have a solution. So it's flipping an idea, taking very simple ideas and trying to see where they lead. Then our best known result was for maps of this following sort. So instead of differential equations, Poincaré told us we could look at Poincaré return maps, looking at finite time maps. So in that spirit, we spent a lot of time looking at one-dimensional maps. Here's a map from an interval to itself. And so these kinds of maps are piecewise expanding. Piecewise expanding means that if you take an interval, a small interval, and you see where the interval maps to a bigger interval, so it stretches. Unless it's around that turning point, around the middle of the interval. But basically, this is a piecewise expanding map, meaning that the slope is everywhere expanding. And so this was a topic which involved invariant measures and a certain amount of ergodic theory, none of which I had ever studied. And he came from Poland, and he outlined exactly how he wanted to prove this, but there was a little glitch, a little deficit, which he couldn't prove. So let me go on, and this is another example of one of these piecewise expanding maps. It doesn't have to be continuous, just each of these pieces is expanding, and as many pieces as you want, but everywhere the derivative is actually greater than 1, actually is bounded away from 1. And so the result was this paper on the existence of invariant measures for piecewise monotonic transformations. Now, this is one funny aspect of these. When I look back at my old papers, I would be a fierce editor and change everything. But for example, I've been emphasizing to you that it's piecewise expanding. If the title of the paper says piecewise monotonic, that's basically a mistake in the title. I mean, it's not wrong, it is monotonic, but that misses the whole emphasis. So a better title would be on the existence of invariant measures for piecewise expanding transformations. Okay? And so what we proved is that there would be an invariant density, which means that there's a statistical regularity of the behavior. So that if you have a trajectory, given any interval, you could say, what fraction of the iterates lie in that interval? So we look at the first 1,000,000 iterates and we say, well, 1,000 lie in there. And then we look at the first billion iterates and we say the first 1,000,000, that's a million of the billion iterates are in there. And there's a statistical regularity which would hold for every interval. So what we proved is that there was this invariant density. Strictly speaking, absolutely continuous invariant density. And he knew which Banach space we were going to analyze this thing in. He knew that we were looking at the densities of bounded variation, and that the whole thing worked out. I described this in this wonderful book, which very well done. all I did was he had only the simplest examples he could cover with his methods, and so I was able to prove an inequality which filled the gap, and we proved the whole thing, that anything with piecewise expanding maps would have statistical regularity. One could say that a better title would be, well, piecewise expanding creates uncertainty. So if you know where a trajectory is with a certain uncertainty, then after each iterate, you lose precision as to where it'll be. That's what the piecewise expanding does for you. So if the slope was 2 and you had an epsilon interval, then after one iterate, there'd be a 2 epsilon interval. So you'd have half the information as to where it would be. And you keep on iterating and you keep on losing the information. And as a result, that's chaos. But the chaos implies the statistical regularity. So piecewise expanding is one way of defining chaos, at least for these one-dimensional maps. So my first paper on chaos was another couple of years later, and we didn't have the concept of chaos, but had we known it, this would have been a good title for the paper. Chaos implies statistical regularity for one-dimensional maps. And you might ask, well, what is chaos? There's a 2,500-year-old parable in the Buddhist literature about the blind man and the elephant. And when I've talked about chaos, sometimes half the audience will have heard about the parable of the elephants and the blind man. And basically what it's saying is, well, you see this fellow holding onto the tail. He says the elephant is like a rope. An elephant is like a rope. And the one holding onto the tusk says, no, it's like a spear. The elephant is like a spear. And one holds onto the leg. No, the elephant is like a tree. And they all have different ideas about what the elephant is. And they are all correct, but they have a partial view. And chaos is something which everybody is familiar with. Popular movies are familiar with. There's Run, Lola, Run, or is a German movie, where they go through the same story 3 times, but they make a little change in the beginning. And there are totally different consequences, because tiny changes initially result in huge changes. We all know you make one mistake driving, and your world could come to an end, shall we say. Or you might crash, and then you're late for your interview for a job, and you don't get the interview. And then in America, you starve to death. In Poland, you probably wouldn't starve to death. You might freeze to death, I guess. I don't know. But so I can't give you a single definition of chaos, but one kind of working definition would be this piecewise expanding. And a topologist would come up with one kind of a definition, and a physicist would come up with a different definition, and they're all talking about the same thing, the uncertainty that we all live in. And I've said many times that perhaps these mathematicians and top scientists were the last people to know about chaos. Scientists didn't discover it. A woman told me that she couldn't come to one of my lectures one time about chaos because the plumber was there, and she had 3 kids, and they were working on both of the bathrooms. And to me, that sounds like chaos. You don't know what's going to happen. You can predict in the short run what's going to happen, but you can't predict in the long run. So remember the elephant. So here is another one of these aspects of chaos that can be used for defining chaos. There's something called Devaney chaos, where Devaney came up with the definition. But basically, Professor Lee, who was my student at the time, has come and given a talk in this series. And he and I wrote a paper called Period 3 Implies Chaos. And this seems to have introduced the word chaos as a mathematical term. The Americans did not have a very good definition of this. Stephen Smale would talk about axiom A behavior, which is not really an everyday term. And the Russians would talk about stochasticity. So they had a well-established term for chaos, stochasticity. But it really suggests the wrong idea, and they have given up that idea and they switched to chaos. So, I cannot tell you how many people have told me how bad an idea the word chaos is, because they never explain why, but there are no better terms. So this whole field is chaos has a lot of different ways of describing it. And one of the things we said is that suppose we have a mapping on an interval. This is what our theorem said. And there's a period 3 orbit. So suppose there is some initial point in the interval, and if we apply the mapping, so this is x0, and if we apply it, we get to a point x1, and then x2, and then x3 is back where we started, well, 0, 1, 2, 3. And if that's a period 3 orbit, now, what we proved is that for every period, like 17, there will be some initial point where you will return to that point after time 17. If you have a period 3 orbit, then you have all of these different periods coexisting. Under what conditions? Well, we have a continuous map on the interval. That's all. Then period 3 implies all of these different periods. So you must have infinitely many different periodic behaviors. And most behaviors would not be periodic. So this is one way of characterizing chaos, to say that there are lots of periodic points of different periods. So Devaney chaos, I'm not giving you a technical definition, but basically it includes the assumption that there are infinitely many periodic orbits, and also that there is one trajectory which bounces around. It's aperiodic, and it comes arbitrarily close to every point in some set. And in there, you've got a dense set of periodic orbits. So this random trajectory will explore the entire region, some entire region, in which all the periodic orbits lie. And those two, the idea of this trajectory exploring all possibilities is a standard idea from statistical mechanics, where it's an ergodic hypothesis. So I've told you now 3 results that I worked on with Lasoty to give you an idea. And my current work is, in a way, an exploration of a similar kind of an idea. And my collaborators, Saiki, Senwan, and Takahashi, are working on this with me. So, when we looked at these questions about the existence of solutions, we're looking at pretty simple ideas. And our goal is always to try to look at simple ideas and not to explore them in as great depth as is possible, but simply to say, here is an interesting result. So, to illustrate this, Hardy and Littlewood, who were famous mathematicians from 100 years ago, were described as simple-minded and muddle-headed. Muddle-headed means confused. So if you look at the entire picture, you're likely to be confused. If you look at a very simple case, which is what mathematicians tend to look at, these both guys are mathematicians, then you're being simple-minded because you're looking at too simple a case. And so my choice, when possible, is to be simple-minded and look at too simple a case rather than a huge case where we are muddle-headed. An example of our muddle-headed work, however, was we looked at a weather model. We wanted to we borrowed a weather model from the United States National Weather Service. And this was a little bit out of date, an old model, and it's had 3 million variables. So you had a grid covering the Earth. This is a whole Earth weather model. And it had 30 layers. So if this was a grid point, if Katowice was a grid point, then you would have to tell what the temperature is and the wind speed and the ozone. I don't know why ozone, but it's in the model. There are 6 numbers you need for each grid point. You say, aha, no problem, we can go out and measure it. But you must also do this throughout the Pacific Ocean, the South Pacific Ocean. Because if you're missing these numbers, the model simply will not run. And then you need to know what the wind velocity and temperature is 100 meters up. Now that's more difficult. And 200 meters up, and 300 meters up, and 400 meters up. You need all this data. And so our question was, how do we update? Suppose we had a reasonable estimate of the weather yesterday. Today, we need to incorporate all the information from the airplanes and weather balloons, weather stations, and put it into the model. And we don't have enough data to cover every weather, every grid point. So we basically developed a technique. We wrote a dozen papers on this about how to update the model, and it was based on the instability of the atmosphere. The idea was that if we look at a region such as Poland, the weather is unstable, but it's unstable in many fewer dimensions. So if we had, for example, 100,000 variables representing Poland, the region of Poland, perhaps it was only unstable in 1,000 dimensions. So you can imagine some kind of a space. I'm trying to wave my hands to draw that you've got this big 100,000 dimensional space. You've got the picture, and it's kind of stable in all the directions except 1,000. And if we could get enough data to tell us what's happening in this 1,000 dimensions, that's good enough. And that's how we developed this. This is an example of being muddle-headed. We don't really understand very well what's going on. But another aspect of this is that it might be unstable in 1,000 dimensions, but Ukraine might be unstable in 2,000 dimensions. So the degree of instability changes from place to place. Okay? So heterochaos is different from chaos. Chaos was when we had this piecewise expanding map. It's unstable in one dimension. Well, you only have one dimension in this case. But what happens if you have 1,000 dimensional instability in one place and a 2,000 dimensional instability in another place. People have faced chaos situations like this. But that's what we want to explore. And even 1,000 dimensions is unstable, is far too above. People have been coming up with mathematical examples which explore some of these ideas, but trying to understand the models is extremely difficult. So my goal in this particular work was, what is the simplest example where you can have multi-chaos or heterochaos, heterogeneity in the chaos, unstable in one dimension here and unstable in 2 dimensions over here. It's the simplest example we can come up with. So this is in the spirit of Lasoty when we were looking 50 years ago at these one-dimensional maps and trying to understand what happens with a one-dimensional map. It seems nice after 50 years to look at what happens if it's slightly more heterogeneous. But to illustrate the difficulties, instead of a 3 million dimensional model, here is a model that Edward Lorenz came up with in 1996. This is a differential equations model, which is very simplistic. The idea is you have the globe of the Earth, and you take a circle, and you take n points along the circle, and the weather is rotating through this region. And realistically, this is not a good weather model, but the idea is to try to understand what happens. He looked at n equals 40, and he's ignoring what happens in other parts of the sphere. So it's really a mechanism. This is not going to make meteorologists enthusiastic about this, but rather it's great for the physicists and the mathematicians who want to explore chaotic models, which are fairly simple to write down, but are moderately high in dimension. So we looked at an 8-dimensional one, and you take an initial condition and you follow it, and you get some kind of an attractor, a chaotic attractor. This red blob is a representation of the attractor. It's a projection onto 2 dimensions. So we're just plotting x1 and x2 and seeing what happens. And we found in that, or actually my collaborator Yoshi Saiki, found 3 trajectories in this. One was one-dimensionally unstable. So if you follow the periodic orbit, things are spreading out in 1 dimension. Found another periodic orbit, also apparently in the attractor. You come back after one time, and it's spreading out in 2 dimensions. And it's stable in the others. And then he found one which was unstable in 3 dimensions. You come back, things are moving away in 3 dimensions. Slower in 8 dimensions, so it's plausible. And just the difficulty of trying to even show that these 3 periodic orbits are in the attractor is really beyond us. We can look at a projection like this, we can choose different variables. It always looks like the 3 are in the blob, but that doesn't say it's really inside. You can imagine everything lying on the surface, and then these things are inside, the attractor is on the outside. And so even this, 8-dimensional, very easy to write down, very hard to demonstrate anything with precision. So this is a low-dimensional paradigm, but we need something a lot simpler than this. And let me skip that. So in the 1930s, the Baker map was published. And the Baker map, 1933, was the idea is, suppose you have a two-dimensional piece of dough from which bread is made. And you take this dough and you squeeze it down and it stretches out 3 times as long. And then you cut it and and then you pile the 3 pieces up. This is the baker method. And so the idea is that A, for example, A is this piece of dough which is getting spread out, not rotated, it's getting spread out and put back into the same region. And usually people use a two-dimensional representation, a 2-piece model, but Seidel talked about 10 pieces, 10 slices. And if we're going to talk about a baker, I guess the dough ought to be 3-dimensional. So here's another way to do it, is on the right, you have this piece of dough, and you cut it, you squeeze it out, and into something very flat, and then you cut it into 4 pieces and pile these pieces back up. Now, on this picture on the right, boxes keep coming up in this discussion. And if you bought a new pair of shoes, they would come in a box. And A, B, C, and D are these tall shoe boxes. So the height is 1, but it's much smaller than that. But each shoe box gets squeezed down into America's favorite food. Pizza. Is pizza a favorite food in Italy? Certainly in Italy, but in Poland, people have pizza shops everywhere? Yes? Yes? Okay. So on the right, we have the boxes that the pizza come in. They're pizza boxes. So you take a shoe box and you squeeze it down into a shoe box, and then you pile them up. And this is a dynamical system. And so you can take one particular point in one of these regions and follow it through this process, and you keep on iterating the process, and your typical trajectory will travel throughout the cube. So you can also talk about the inverse process, which is harder, where you take the pizza box and you squeeze it into a shoebox. But what's happening here is that each region is expanding in 2 dimensions and it's contracting in 1. So it's expanding in the 2 horizontal dimensions and it's contracting in the vertical direction. And so this would be a classical type of thing. I've never seen this before. We created this example, but it wouldn't surprise anybody as an example. But we decided to change it a little bit. So we're back to a 2-dimensional model for a moment, where our set A maps to the bottom half of the square. So you're going to squeeze it down, it increases in area. D, you squeeze it down, it increases in area, goes to the top half of the square. We've already covered the whole square with A and D. And then B, so what's happening? A and D are both one-dimensionally unstable. They are horizontally unstable and vertically they are stable. But C expands in both coordinates and C gets mapped onto the entire square. Okay? And B gets mapped onto the entire square. Now we have a dynamical system, which is, you could say, heterochaotic. Heterogeneously chaotic, multi-chaos. Because in one part of the space, it's one-dimensionally unstable, in A and D, And in C and B, it's two-dimensionally unstable. And these regions interact. So if you take a random point, what you would hopefully see is that if you follow this trajectory, it wanders throughout the entire square as you iterate after iterate. So this is a simple-minded model of the atmosphere. Instead of 3 million dimensions, it's 2 dimensions. And this gives us a much better chance of trying to actually show what's actually happening. I should also say that it has the interesting property that almost every initial point will spend, well, the Bayes measure is invariant. What that means is that if we take any little square, which might represent 1% of the total square, and we ask what fraction of the time will each trajectory spend in there, it would be 1%. Almost every point would spend 1% of the time in there. Statistical regularity. That's what we started with in example 3. So this, we would hope to have this kind of a property. The nicest dynamical systems that people look at are called subshifts of finite type on some finite number of symbols. I don't think I would describe that, but basically this doesn't have that property. This has all kinds of nasty properties, and that's what makes it interesting mathematically and physically, that it has these weird properties that one would not anticipate. So now, we realized we could increase this model into a 3-dimensional model. See, the first model had the property that any point in the right-hand side of the square would be the image of 3 different points from A or D and from B and C. The mapping is 3 to 1. 3 points go to 1 point. This is a bit embarrassing. So what we have done over here in this 3-dimensional model is that we've added the vertical variable y. So that now we squeeze it down, and A, for example, goes to a pizza box. So no, my mistake. A is a pizza box. It's a square. And A goes to A prime, which is a shoebox shape. D goes to D prime. B goes to B prime, so on. So the B and C are shoe boxes which get stretched out into pizza boxes. The dynamics on the top is just like the dynamics on the top is just like the dynamics of the square. So this is we've simply added a dimension, and this preserves volume. So we have a volume preserving model which has this property that exhibits this. Again, it's 2-dimensionally expanding in some regions and 1-dimensionally expanding in the other. The dimension we've added is this y variable, and it's contracting in the y dimension. So one can write down some equations for this, but the picture is worth 1,000 words. So we've been able to prove a theorem, and the theorem says that well, there are periodic orbits which are 1-dimensionally unstable, basically unstable in the x direction. There's a dense set arbitrarily close to every point in the cube. There's a periodic point whose orbit is 1-dimensionally unstable. Not 2-dimensionally unstable, 1-dimensionally unstable. and also arbitrarily close to every point, there's a periodic point which is two-dimensionally unstable. Okay, so you picture this. All of this is coexisting. It seems really impossible to picture how anything so complicated could actually exist. That's the advantage of looking at this. That arbitrarily close to every point, you've got something which is only one-dimensionally unstable, and also arbitrarily close, there's stuff which is two-dimensionally unstable. And you know what this map is, so there's nothing hidden about the complexity of the system. And there's also a trajectory, actually for almost every initial point. If you follow the trajectory, it'll get arbitrarily close to every point in the cube if you wait long enough. It gets close and then goes away. And then wait along, it gets closer and it goes away. And later on, it gets even closer. It gets arbitrarily close to every point in the cube. So we can call the entire cube an attractor. Well, that's it's chaotic. So it's like the Devaney chaos where you've got a dense set of periodic points, but this has two different dense sets of periodic points. And this, to me, is a model, simple-minded, a simple-minded model of what's actually happening in the Earth's atmosphere. In fact, most complicated dynamical systems seem to have this property, where the different regions will be unstable in different numbers of dimensions. The atmosphere might differ by 1,000. You might have one which is 1,000 dimensionally unstable, another region which is 1,001, and another region which is 1,002 dimensionally unstable. Throughout the world, you'd have all these different kinds of behaviors coexisting. How do they coexist? That's what we want to get. How can you actually come up with a model which has this picture? And so, this has been a long path of trying to prove that these things actually have this property. So, one can just state what happens here, but it turns out that it's surprisingly difficult. A standard technique is for proving the existence of periodic points in these traditional Baker maps would be to find a cube B, and as you apply the mapping to the cube, it expands horizontally in 2 dimensions, so that after k iterates, your box expands to the entire width in both directions. The box B has to be chosen just correctly for this to work, and so you get a pizza box image. 2-dimensionally wide and very small in the y direction. Whereas if you go backwards in time, you get the red box, which is a shoe box. It's actually a spaghetti box. But I guess that would be a better analogy, wouldn't it? Pizza and spaghetti. So the red box, which is the shoe box, and the blue box, which is the pizza box, intersect. And you can show with simple arguments that if you have this configuration, then there's a periodic point where they intersect. And that periodic orbit must pass through the box B. So you now have that the box B has a periodic point. And if you can show this, that there are many of these boxes, in the case of the Baker map, it's very easy to show there are many such boxes that can be picked. But in this case, it's actually quite difficult to show that the box can be picked. And after a couple of months, I thought I had a proof, and then I found that there was a hole in the proof, and I had to extend to fix the proof. this is just a statement of showing how for the Baker maps you can pick these rather easily. So then one has to prove, so the periodic orbit that you would establish here, you can see that it's mapping from the shoebox to the pizza box, so the periodic orbit would be unstable in 2 dimensions. Now, if we can show there are lots of these little cubes, then we can show that arbitrarily small cubes, we can then show that the periodic orbits, which are 2-dimensionally unstable, are dense in the whole space. Now, I'm also showing you F and F inverse. F is the mapping. F inverse, well, the mapping F maps 2 pizza boxes and 2 shoe boxes to 2 shoe boxes and 2 pizza boxes. The inverse does the same thing. Shoe boxes go to pizza boxes go to shoe boxes. And these are virtually, topologically, they are identical maps. And as a result, if we can show that the F inverse also has a dense set of 2-dimensionally unstable orbits, if an orbit is 2-dimensionally unstable going forwards in time, going backwards in time, it's contracting in 2 dimensions, and it's unstable in 1. And so one winds up with a complete picture. Showing that the dense trajectory is just an additional complication. And so we would define heterogeneous chaos or multi-chaos as having a set where there's a dense trajectory, or almost every trajectory is dense, and there's a dense set of periodic points which has a particular unstable dimension, and another dense set which has a different unstable dimension. And so that's what we've established with this particular case. We also go on and prove ergodicity, which I won't tell you about. It's even more technical. But these are topological ideas, and the ergodicity is measure theoretic ideas. It all fits together. Now, in trying to create this example, our goal has not to look for generalization and see how many different ways we can change this example. Rather, it has been to be simple-minded and say, here is an example. A, B, and B, these are all width is 1/3. We haven't looked at what happens if it's 2/5 or different sizes. We leave that to other people. It simply says, this is an example which is really simple, and the more we look at generalities, the vaguer it's going to become to the audience. So this is the end of my simple-minded presentation. So thank you.
So we have time for questions, comments.
The question concerning mixing product of this heterogeneous Baker transformation is mixing or not?
I can say yes, it's mixing or not, right? There are a wide variety of properties we have not explored. We would believe that it's mixing. Okay, but we do not have a theorem saying it's mixing. Okay, so in my original paper with Lee on period 3 implies chaos, half the theorem was about the fact that it's mixing, but we have not applied it to this particular system, and somebody should.
Okay, further comments, remarks?
I'm a physicist, that's why my question probably will be very naive. But what is the effect of noise stochastic noise on the properties of for example, the periodic pairs or multi or this type of heterogeneous multi-class. I mean, because when I read the book of Lasoty about probabilistic properties of chaotic systems, sometimes it happens that the noise somehow either blurs out or stabilizes the effect. So how would it be here?
I would expect the noise to simply maintain the chaos. Now, I have recognized for the last 50 years that noise is tremendously important. But just as the Russians started out with the term stochasticity, which seems to suggest noise, they were using stochasticity as a term to talk about chaos where there was no noise. And so I have felt that for me, it's best to try to separate out the chaos, the deterministic chaos, from the stochastic properties of noise. But it's a very legitimate question, and it would appear here that the noise would simply increase the distribution of dynamical behaviors. Right now, you have trajectories winding throughout the entire space, and it would be hard to see how that would stop because of noise. Okay. So, interesting question. Anybody else?
Let me say one comment that in the case of noise can stabilize the problem, but also destabilize, because it depends on what kind of noise you consider. If you consider additive, you have a multi-dimensional equation, you consider additive noise to each coordinate, so you frequently stabilize. But if you consider you have two-dimensional system and you stabilize one variable, add noise to one variable, not to the second, so you can destabilize everything. Okay, so another comment.
As I remember, you have shown that there is no translation of this chaos into on form of subject of form symbols. Yes, something like that. It was. There is.
Are you asking what we showed about the?
Yes, that there is no transformation from this system to subject and form symbols.
So let me explain that remark, okay? Suppose a trajectory starts in the box A. And that makes the vertical direction contract by a factor of a third. So it goes from full height to 2/3. Now, let me say it another way. I want to look at the horizontal variable. Look at, it starts in A, and goes to A prime, which is half as wide. And if you apply A 10 times, it gets contracted 10 times. So it's contracted by a factor of 2 to the 10th. B and C are expanding, but if you go through 9 expansions, so your width is originally from 0 to 1, you contract 10 times, you're now from 0 to 1 over 1,000. If you then expand, you go from 0 to twice as big, 0 to 4 times as big, 0 to 8 times as big. And the only place you can expand is in B, not C. So after 9 of these expansions, you're still going to be in B. You cannot apply C because you don't intersect. Okay? So if you go through n contractions in the region A, and then you go through n minus 1 contractions in B, you're still going to be in B, you're not going to be in C, and you cannot apply C. But if you go through n expansions, then you can apply C. So whether or not you can apply C depends on the last 2n iterations. Okay? I'm sure this is not clear, but
my question is that maybe you consider higher dimensional subshapes, for example, fifth dimensional, or six or so on. So whether it is possible to describe these dynamics in terms of higher subshapes or higher dimension.
right. Well, I think what I'm saying is that if you look at iterations, 2n iterations, that's basically looking at 4 to the power 2 to the n. Subsets of length 2n, and you don't get, you do not know what happens next unless you know what actually happened before. So in any case, we have in no sense exhaustively looked at the question of subsets of finite type. And so we leave it to others.
Okay, further questions, comments?
Thank you. I would like to mention one thing. Sorry, see. 30, maybe 40 years ago, I had attended a lecture which was given by Carl. I think that many of you know this name. So Professor Carl in one center showed us an example where he had from one side chaotic motion and from another side a stochastic signal, let's say, the realization of stochastic process. And he postulated that it's impossible to distinguish if it is chaotic motion or if it is stochastic signal. So this question, I think, is still open. It was his proposition in that time. And my second comment is just a question. Usually, the guys who are dealing with the chaotic motion are assuming that they know something about Laplace exponent. So my question will be, if we have this multi-chaotic motion, so can we understand that we have switching, for instance, from 1D to 2D periodic points, that we have more or less Laplace exponents? Some comments to this term.
Right. So in the book I wrote on chaos, the definition we used for the primary term we used in defining chaos there was that there are positive exponents, one or more positive exponents. That's the way we define chaos. Here we can calculate the Lyapunov exponents exactly. We take the point of view that the Lyapunov exponents are what a scientist could use if you have a numerical model. And so this is like the elephant, that the Lyapunov exponents are one aspect, and it's important for the physicist who has a model. For the topologist, this idea of these periodic orbits being dense is another aspect that I've emphasized here. But in this particular case, let's see, I think there's one positive exponent and two negative exponents, but you can change the model a little bit and reverse those numbers without changing the dense properties of this. In particular, this might be an exception to your colleague's notion that you cannot distinguish between the chaos and stochasticity, because if we had a trajectory we were following and we had 10 A's in a row, we would then know that we could not get a C for the next 10 iterates at least. And so that would say that it's not just noise, that there's because you could make a bet that for the next 10 iterates, you won't get any C's. So I would say that this might be an example, and it's exactly this finite, this thing that I've been unclear about the finite subsequences. Finite subsequences are basically stochastic type properties in deterministic chaos systems. And the fact that this fails to have the dynamics of finite subshifts means that it's a really interesting system.
Okay, and other questions, comments? Around, I don't see. So let's thank our speaker. Thank you.
Thank you everybody for coming, and we invite you to coffee in the foyer, all of you. Thank you once again, Professor.